All right, today we're diving headfirst into one of the deepest, most mind-bending questions in all of science. Seriously, it's a story about a mystery that goes right to the heart of reality itself, challenging our most basic ideas about how the universe works. We're going to see that reality is, well, it's a whole lot stranger than any of us could have imagined. So let's get into it. You've probably heard this phrase before, right? In business, in life, it's this fundamental trade-off. And it turns out it's a great way to think about physics too. It gets at this really simple but powerful idea. Sometimes you just can't have it all. Some combinations of things you really want are just impossible. And this very idea, this impossible trio, is the perfect way to start thinking about a massive puzzle at the very core of our universe. Okay, so let's jump into the first piece of this puzzle. It all starts with a very famous experiment that has been the gateway to the completely baffling world of quantum mechanics for almost a century now. It's a case where tiny particles start behaving in a way that just seems, well, impossible. So, to really get this mystery, imagine you're firing tiny particles, like electrons, at a wall with two little slits in it. If you fire just one, it lands at a single definite spot on the detector screen behind the wall. Kind of like a tiny bullet. Makes sense, right? Simple enough. But here is where it gets incredibly weird. If you fire thousands of them, but one at a time, you'd expect to see two clumps behind the slits. But you don't. Instead, you get this striped pattern. It's called an interference pattern, and that's something you only get with waves, like water waves, that can go through both slits at the same time and then interact with themselves. And that is the question that just completely baffled physicists for decades. I mean, think about it. We're firing these electrons one by one. There's nothing else for them to interfere with. So how on earth does any single electron all by itself know where to land to help build this wave pattern over time? It's almost as if each particle has to be going through both slits at once. And that contradiction, that's the quantum mystery right there. Now, this level of weirdness, it did not sit well with everybody. And it especially didn't sit well with Albert Einstein. He was just deeply, fundamentally troubled by the whole probabilistic, almost mystical nature of quantum mechanics. He was convinced there had to be something more sensible, a complete reality hiding underneath all this strangeness. Einstein's idea of a sensible universe really boils down to two common sense principles. We call this combination local realism. First, there's realism. That just means a ball is red even when you're not looking at it. Its properties are real and definite, whether we measure them or not. Then there's locality. That says that if you want to affect that ball, you've got to either touch it or send some kind of signal to it. A signal that can't travel faster than the speed of light. No instantaneous action across the galaxy. It all seems pretty reasonable, doesn't it? So this is the big showdown, the fundamental clash of worldviews. On one side, you have Einstein arguing that the universe has to be deterministic and local. He thought quantum mechanics was an incomplete picture, that there had to be some hidden variables, some unknown properties of particles that were secretly telling them what to do. But on the other side, quantum theory says, nope, the universe is fundamentally random, it's based on probabilities, and this is the really disturbing part, it's non-local. And this is Einstein's famous, almost contemptuous phrase for the strangest prediction of quantum mechanics, entanglement. This is the idea that you can link two particles so that measuring one instantaneously affects the other, even if they're on opposite sides of the universe. To Einstein, this was just pure absurdity. It was spooky action at a distance, and it couldn't possibly be real. So for decades, this whole debate was just philosophy. Was reality local and sensible, or was it spooky and weird? It seemed like there was no way to ever really know. But then, a brilliant and kind of unsung physicist named John Stewart Bell came along and figured out how to drag this argument out of the philosophy department and into the lab. He turned it into a question that science could actually answer. Bell came up with something called a no-go theorem. And hey, remember our good, fast, cheap analogy from the start? A no-go theorem is basically the mathematical proof of that idea. It proves you can't have it all, that certain sets of properties just don't go together. And Bell's theorem, specifically, is a no-go theorem for Einstein's worldview. It proved, with pure math, that you cannot have a universe that is both local and has all those hidden variables determining everything. You have to pick one. You can't have both. And here's the genius part. Bell didn't just leave it as a philosophical proof. He translated his theorem into a concrete mathematical test that you could actually perform in an experiment. It's called Bell's inequality. And what it did was draw a sharp line in the sand. If Einstein's local common sense universe was the real one, all your experimental results would have to fall on one side of that line. But if the spooky, weird world of quantum mechanics was right, the results would fall on the other. So there it was, the ultimate question. For the very first time, we had a way to put reality itself to the test. All that was left was to actually build the experiments and see what happened. Was Einstein right? Or was the universe even stranger than he could bring himself to believe? So, what was the answer? After years and years of incredibly precise, incredibly difficult experiments, physicists were finally ready to deliver the verdict on the fundamental nature of reality. And the verdict was absolutely stunning. Experiment after experiment, each one more confident than the last, showed the exact same thing. Our universe violates Bell's inequality. The data consistently, stubbornly falls on the quantum mechanics side of the line. Einstein's beautiful common sense picture of the universe was wrong. The implication here is just profound, and there is no way around it. That whole worldview of local realism, the idea that things have definite properties before we look, and that nothing can travel faster than light, it's simply incompatible with the universe we actually live in. Our universe is not locally real. So this forces us into a really uncomfortable choice. We have to throw out one of our most basic bedrock assumptions about the world. We either have to give up realism and accept that a particle's properties literally do not exist until we measure them, or we have to give up locality and accept that there are connections in the universe that are genuinely instantaneous, a true spooky action at a distance. Now, while there's still debate, the overwhelming view among physicists today is that it's locality that has to go. Now, you'd think that a discovery that completely rewrites the fundamental rules of reality would be an immediate scientific earthquake, right? But what's so fascinating is that the true impact of John Bell's work took decades to be fully understood and appreciated. I mean, just look at this timeline. Bell publishes this incredible paper in 1964, but for almost 30 years, it was basically a niche topic, something debated by a small handful of physicists who cared about the weird foundations of quantum theory. It really wasn't until the 1990s that the wider scientific community woke up and realized what a bombshell this was. So why the long wait? Well, for one, most physicists were just busy using quantum mechanics. I mean, it works spectacularly well for building things like lasers and computers, so they weren't too worried about its philosophical problems. Plus, the experiments themselves were just insanely difficult to pull off. But really, the deep philosophical questions Bell was asking just didn't seem as urgent as solving concrete practical problems. And here's the beautiful irony. That spooky, seemingly philosophical feature of reality, this thing called nonlocality, has now become a resource. It's not a bug, it's a feature. It's the absolute cornerstone of revolutionary new fields like quantum computing and unhackable quantum cryptography. The very thing that Einstein just couldn't stomach is now being engineered into the technologies that are going to define our future. So we end right back where we started, with a profound mystery. This whole journey, from that weird pattern in the double-slit experiment all the way to Bell's theorem, has forced us to let go of a simple, common-sense view of the world. It suggests that reality isn't some fixed, passive thing out there for us to observe. It suggests that reality is something that is fundamentally shaped by our very interaction with it. And that leaves us with one final lingering question. What does it mean to live in a universe whose deepest truths are only revealed when we dare to ask the most impossible questions?